So I was about to redo the solutions for practice exam A, and then I thought maybe you'd like to see how that goes. So I'm just going to go through the exam and show you how I do all the problems. It'll take me longer doing it this way than it would have otherwise, but I hope it's useful for you. So problem 1 says that the heavy box is initially at rest at the top of a ramp. Okay, so here's our ramp, and here's our heavy box. So it's initially at rest, and then a girl pushes the box down the ramp. At the bottom, she stops pushing, and the box comes to a stop due to friction. Okay, so she pushes the box all the way down the ramp, and the box is moving with some speed v, and it goes over here and comes to a stop. So v final is 0. For the entire process, the work done by the girl on the box was blank, and the work done by gravity on the box was blank. Okay, so if we look at my formula sheet here, work, the definition of work is the force dotted with the displacement. So this is the path. So this is the path that the box takes. It goes down, and then it goes horizontal. So that's the way it moves. So if we look at work equals F dot delta R, the sign is determined by this dot product between the force vector and the instantaneous displacement. So the box is always moving this way, and the girl is always pushing in the same direction. So her push force, so the force from the girl, is in the same direction as each delta R. So her force should be positive. So during this interval, when it's flat, gravity is doing no work because the force of gravity is down and the displacement is in this direction. So that dot product is 0. But while the box is moving down the ramp, there's a component of that displacement, delta R, that's in the same direction as the gravitational force. Oops. So since this angle is less than 90 degrees, this will give us a positive dot product. So the answer is A. Okay, so how about problem 2? You suspend a weight from a 30 centimeter wire. The wire stretches by a centimeter. You cut the wire in thirds. You discard one piece of wire and suspend the same weight from 2 of the 10 centimeter pieces of wire. How much does each 10 centimeter piece of wire stretch? Okay, so whenever I see these problems where you're sort of comparing two scenarios, I figure out what formula applies. So in this case, this is a Young's modulus stress strain kind of thing. So we're going to be using this equation. So let's just write that down here. So force per area is the Young's modulus times delta L over L naught. Okay, so whenever I'm doing these kinds of problems, I write down the equation for each case. So over here for this case, let's say this is case 1 and this is case 2. So for case 1, F1 over A1 equals Y1 delta L1 over L naught 1. And for case 2, we have F2 over A2 equals Y2 delta L2 over L naught 2. Okay, so now I start looking to see if any of these variables are the same. Because this is true for this mass, and this is true for this mass. So let's see. So the force exerted on each of these scenarios is Well, over here it's mg because it's the force of gravity. It's going to be equal to the force of gravity that's acting on this mass. And it's going to be the same over here. So over here we have a choice. We can either say, okay, the cross-sectional area is bigger because there's two wires, or we can say that each wire is supporting half of this mass. So whichever you prefer, you can do. I think I'll go with the area. So that means that the force of gravity on this block is also mg. So these two forces are the same. So we'll say that F1 equals F2 equals F, which is just our applied force. So those are the same. So I can basically go in here and just get rid of these little subscripts because these two F's are the same. So how about area? Well, if this mass is hanging off of something with cross-sectional area A1, this mass has two of them. So the area that's relevant for mass 2 is actually twice the area of this one. So I know that these look really skinny, but in reality these wires are little cylinders and they have cross-sectional area A, and we're saying that this one has cross-sectional area A1. This one has two little cylinders, so it's got two like this. So the total cross-sectional area is A1 plus A1, which is equal to 2A1. And that's our A2. Okay, so now we know that A2 equals 2A1. So these are different. Now how about Y? So Y depends on the material. This was the same wire. We just cut it, so it's going to have the same Y. So Y1 is equal to Y2. And we can again get rid of these little subscripts. Good. Okay, so how about the delta L1? So delta L1 is something that we're given. So it says the wire stretches by 1 centimeter. So that means that delta L1 is 1 centimeter. Good, and we're looking for delta L2, so that's what we're after. So we don't know that yet. How about the original length? So the original length is 30 centimeters. And the original length of this is a third of that. So the original length for wire 2 is a third of that, which is 10 centimeters. Okay, so now we're ready. So let's just rewrite these and fill in everything that we know. So we knew that the F's were the same, but we don't know what F is yet, or maybe never. A1 is fine. Let's do everything in terms of the ones. So A1 is A1, and then we have Y. Delta L1 is 1 centimeter, and this is 30 centimeters. Okay, so over here to the next one. So F2 is just F. Now we need to write A2 in terms of A1. So A2 is 2A1, so we just plug that in here. That's Y, and delta L2 is what we're looking for, and we know that its original length was just 10 centimeters. Okay, so now we're after this, but we have F and Y in both equations, and A1. So what we can do is over here, we can move Y to the other side. So we'll have F over A1Y equals 1 centimeter over 30 centimeters. And over here, we're going to move Y over. So that's A1Y, and I'm going to move the 2 over to the other side. That's going to be 2 delta L2 over 10 centimeters. So now this is equal to this. So that means this is equal to this. And if you set those equal to each other, 1/30 equals 2 delta L2 over 10 centimeters, and you solve for L2, you'll get 1/6. So normally, if you're in really good practice with this kind of problem, you can do this much faster than I just did it. But you haven't seen a whole lot of these in your career, so I wanted to take my time and go through that one. Okay. So let's take a look at 3. The surface tension gamma of a liquid can be found by measuring the force F needed to lift up a circular platinum ring of radius r from the surface of the liquid. Ignoring gravity, circle all that apply. So the surface tension from the liquid tends to pull the ring back towards the surface. That's true, because as you lift the ring up, you're going to get little tension vectors that point down like this and want to keep the ring in place. The force required to lift the ring will increase if r increases. So they're saying if we take this ring and we make it bigger, will the tension force needed to lift increase? So the tension force here is gamma times L. And L is the length of the edge. So if this is the ring, and then you've got water, it's this distance the whole way around and on the inside in this case. It's those two lengths that determine the force. So if you make the ring bigger, you're increasing that little dashed line's length. So that's going to increase the force of tension. So this is also true. The force to pull the ring up will be the same for different liquids. So gamma is liquid dependent, so that's not going to be true. So let's get rid of that one. The force exerted on the ring by surface tension in this case is 2 pi r gamma. So 2 pi r is the circumference of the ring. But this ring has an inside and an outside. They almost have the same radius. Like this one has a radius r, and this one has a radius r plus a little bit. So they're basically the same. So if you add up those two circumferences, you're going to get 4 pi r. So E is also correct, but this one is not, because it didn't take into account that the ring is going to have sticky water collecting on both sides. So there's a little tension in here as well, and on this side too. Okay, so the next one says 2 identical spherical drops of water are falling through the air in free fall. Which of the following actions would decrease the total surface area of these 2 drops of water? Okay, so we know that more surface area takes more energy. So if you want to minimize energy, you need to minimize surface area. So we have 2 identical drops. So we could break the 2 drops into many smaller drops. So if you do that, you're going to increase the overall surface area. I like to think about a stick of butter, or a stick block of tofu or something. So if you take it and then you cut it in half, so you come in with your knife and you cut it in half and break it into 2 pieces, now you've just exposed new surface that wasn't exposed before. So the total surface area has to go up. So whenever you take something and you chop it into smaller bits, you're increasing the total surface area, which means you're increasing the energy. So this will do the opposite of what the question's asking for. Okay, so distort one of the drops into an elliptical, non-spherical shape. So spheres minimize or maximize the surface area to volume ratio. So it is the shape with the lowest surface area that you can get for that volume. So if you distort it, you're actually going to increase the surface area. So we don't want to do that. Decrease the surface tension of the water by adding a surfactant to both drops. So that would definitely decrease the energy because it's going to break up the little bonds that are on the surface and make them less sticky. So that one's good. Combine the two drops into a single larger spherical drop. That is good because it's the opposite of A. Combine the two drops to form a long, thin tube of water 1 meter long. Also not good because we know that the spheres are going to minimize the surface area for that volume. Okay, moving right along.